constant of an acid. And Ka is the common symbol for that. And it will equal the activity of the hydrogen ion, approximated to the concentration, times the conjugate base concentration. Like that. And that equilibrium has massive consequences for our biology. So acid-base strength, we have here the different strengths of the different acid. We just already said that there's strong acids and everything else is weak. But now within the range of weakness, some things are more weak than others. And so, for instance, on this list they have that as acids go, the strongest acid listed up here, HCl. And now, a weak acid would be carbonic acid or vinegar, phosphoric acid, in an order of decreasing, or in this direction, increasing acidity. How do you, what do you do to give a number to that? Ka. If the Ka is a large number, is it more or less acid? So if the Ka is large, is the hydrogen ion high or low? Because it's not divided by anything, if this is large, this is large. Ka large, therefore the hydrogen ion concentration is large. What if the Ka is very, very small? That's going to be small. So if the Ka is very, very large, then you have a stronger acid. If the Ka is small, you have a weaker acid. So this would be a stronger acid, and this is a weaker acid. This is all reviewed in your textbook also. You take a look at the diagrams in there. Okay, so substances that are said to be negligible acidity just means that they don't fall apart at all, not even weakly. In that case, we say that the conjugate base is strong. The conjugate base, the thing that got left behind when the hydrogen took a trip. If the conjugate base never lets the hydrogen ion go in the first place, no way, no how, you're staying with me, hydrogen ion, and I'm not letting go. That's a very strong conjugate base. A weak conjugate base is like the chloride ion that says, get out of here, hydrogen ion, in the first place. Get out of here. Alright, so our acid-base strength, we have the hydrogen ion coming off, leaving the conjugate base behind. In this particular example, where we only have the single arrow, that HCl was actually an aqueous phase, so it would have been hydrogen ion times chloride ion divided by what? We were setting up the equilibrium for HCl in water. We've got HCl as the aqueous HCl. The water rips it apart into the hydrogen ion and the got it on the slide. It shows the reaction with water. I have left the water off and just simply have this reactant present. This is the old-fashioned way to write it. And the new fashion that's coming back. What goes on the bottom? This is a gas dissolved in water here. The HCl is going on the bottom. If it were in equilibrium. But it's not in equilibrium. This is a common exercise that's given to students to try and figure it out. It's not in equilibrium. All of it is associated. What's the concentration of the HCl in water? 0. What happens when you put a 0 down here? You mess up your equation, right? The whole thing just explodes in your face. The equilibrium coefficient can only be used when you have an equilibrium. And so we don't do that with the strong acids. With the strong acids, you can't do an equilibrium coefficient. But now acid-base strengths with things that do have equilibrium. And here we have acetic acid. There's the hydrogen that's going to come off with the water, making our H3O or our hydrogen ion. And acetate, the acetate ion being our conjugate base. Acetate is a stronger base than the water, meaning that it doesn't really want to let that hydrogen ion go. And so it actually has a measurable equilibrium. Here we have the ionization of water done on a pretty slide showing the two water molecules coming together, leaving behind one sad OH minus. Actually, it isn't sad at all, it's happy, it's got the electron. We all know that atoms want the electrons for themselves. The H3O over here, and now we do have an equilibrium. So looking at that reaction equation, we're going to set up our KW. And we know that the KW will equal the hydrogen ion concentration times the hydroxide ion concentration. If we had the equation written as it is on the slide, we must follow the equation that we're given. And so I will write KW equals H3O minus. Same thing. We know that water sitting out on the shelf in a bottle doesn't do this very much. We know that water is water, H2O, covalent stuff. We know that the concentration of this and this are going to be very, very, very low. Therefore, less than 1. Therefore, KW would be expected to be large or small? Small, yes. Just checking your memories there. So the KW is going to be small and much, much less than 1. And yes, it is 10 to the minus 14, a very small number. So this is sometimes how the case of C is written for water, and it is such an important thing that it is written as KW. At 25 degrees Celsius, the KW is 1 times 10 to the minus 14. The equilibrium constant for water, like any equilibrium constant, is ridiculously dependent on temperature. 25 degrees Celsius is the current accepted standard room temperature. And actually, if you sit in a 25 degrees Celsius room, you discover that it's actually uncomfortably warm. were in that room, you'd discover it was actually uncomfortably cold, the temperature of most rooms in England. Okay, so Zoran Sorensen came along and defined something as pH. If we have pH as equal to the negative log of the hydrogen ion concentration, this is the formula that you've all seen before. You'll say the negative log of the hydrogen ion concentration. And again, that's not what Zoran Sorensen actually said. He said it's the negative log of the activity, and that we deal with later. Again, concentration is close enough for our work right now. Why did he do this? Let's take a look at that Kw. Kw equals 10 to the negative 14. That is equal to the hydrogen ion concentration times the hydroxide ion concentration. When we're looking at the autolysis of water, the hydrogen ion and the hydroxide ion come out in equal parts. What is the hydrogen ion concentration going to be? They're going to be equal. The two of them as a product equal 10 to the minus 14. Give me a number. Exactly. It's going to be the square root of 10 to the minus 14. And the hydrogen ion concentration, therefore, is equal to 10 to the minus 7. Be able to do that on your calculators. Your next exam will have at least 10 of these where you have to calculate the square root of something. What Zoran Sorensen found out was that the hydrogen ion concentration in any solution ranges from 10 to the minus 2 and minus 1 to 10 to the minus 14 molar. These are small numbers. It starts with a small number and goes down to an even smaller number. And when working with numbers less than 1, is one without a calculator, without a computer, is one happy? How happy are you guys when you have to plug into your calculator numbers less than 1? Alright? You think having to deal with numbers like 1, 0 times 10 to the minus 14 on a daily basis, it is not a fun thing to do. And believe it or not, back then there was a huge body of math we were all taught, which was how to handle logarithms in a regular arithmetic way. And so, because he knew that all these numbers were just really impossibly small, and people didn't want to go 0.000000643 divided by 0.002476, right? This is not fun. But this is the sort of calculation that you would always have to do with numbers in this range. So he said, we'll just fit into logarithmic numbers.